Good afternoon, everyone. Welcome to another TACO-sponsored webinar in our ongoing TACO Tuesday series. And this is our first one for 2021. Holy moly, thank God it's 2021 is one of the few things I can say right now. My name is Brett Zerba. I'm an applications engineer with TACO, and I will be moderating today's webinar. And the main presenter will be Rich Medairos. Many of you, I recognize quite a few names on the list, have sat in on some of our other webinars, so hopefully you know both of our names anyways, and Rich will give him a nice introduction on himself very, very shortly. Before we get going too far, we always like to do the wave the hand thing, and I see people already waving their hands, so please wave your hand. Thank you, Robert and Mark and others. We know that you can see the frame or Rich's presentation, the first screen, and you can hear us, so that's great. So thank you very much for putting up with us on that one. Hopefully everyone remembers that roughly 24 hours after today's webinar, you will get an email. You should get an email for the one that the email address that registered will get an email from TACO or from the webinar site with access to the broadcast, the recording of today's webinar, as well as access to a PDH certificate. So any PEs out there that need a certificate, and if it qualifies in your state, feel free to use that. And by the way, we are qualified in Florida, so any folks in Florida, if you feel you need some specifics on that, just send us another email and we can get that one upgraded for you. So please keep that in mind. Today's webinar is going to be on hydronic heating plant concept design. I'm sure some of you have sat through the chiller plant concept design, so this is going to be pretty much in the same format. So Rich is going to go over a lot of that information, but please ask questions, right? I'm going to be monitoring the question area, and I will bring them up. Rich will stop periodically. We'll answer as many as we can. And then after the fact, some of you have gotten answers from us after the fact, so we will continue to do that as well. So we are going to continue the webinar series. There's one a month, actually two a month from TACO. One more focused on commercial end of the business, HVAC industry, and the second one is more residential or wholesale end of our business. So through March, we'll have one each of the months. Starting in April, we're going to go back for a few months of doubling up. So you'll have to hear us twice a month, two commercial and two residential. And please, if you have some ideas, email them in or put them in the question area, and we'll try to bring those into some of the classes. That's our goal as we go. As you can see from Rich's slide, we did. Oh my God, Rich, it's 2021. We're almost 101 years old now. TACO is over 100-year-old privately held company, third generation, led by Johnny White. Hopefully some of you have met him or seen him in person. He's quite an individual. So I think that's enough for today's introduction. I think I've got all the details down. Oh, I want to give a shout out. I recognize quite a few names on there. It's a shout out to Adam and Mary and Rudy and Ashraf, Blake and Josh and Glenn and Troy and Tay and Jeff, Jason, Chris, Duke, Stu, Darren, Aaron, and a special shout out to some TACO folks that may be on, Ken and Michaela and Greg, Mario, Victoria, and Tom and Steve. And sorry about the Steelers, guys. Anyways, Rich, take it away.
Well, thanks, Brett, for that great introduction. My name is Rich Medairos. I'm one of the senior systems engineers here at TACO, and I'll be presenting today's topic. Just a quick intro for myself. I am a mechanical engineer, also a registered professional engineer, registered in a couple of states. I specialize in the engineering and design of HVAC systems, and I've been in the business for several years. So we're going to get right into today's topic, which is hydronic heating plant concept design. And I emphasize concept because what we're trying to accomplish is to get people to think through the process. We'll get into a couple of little details, but the real idea here is to develop a thinking process by which to put together a heating plant. And in today's presentation, just to clarify, when we talk about hydronic heating plant, we're talking specifically a heating plant that uses some type of fossil fuel. And we're going to get into those details in a moment. Okay, so I like to put this up, especially when we're talking about equipment that burns fuel, fossil fuel, and that is to say that review and comply with all local and national codes before starting heating plant design. This is extremely important because codes vary throughout the world and there are multiple layers, which is why I put in the phrase national and local. In the United States, there are national codes, there are state codes, and there are county and or city codes. And so there turns out there are 3 or 4 layers of codes that we have to comply with, especially when it comes to fuel burning equipment. So please be aware of the codes before you start designing. So with that in mind, so the topics we're going to cover today is I want to design a heating plant, but where do I start? What type of fuel should I use? Very important. Where do the boilers go and how many do I need? There's primary pumping versus primary secondary pumping. How many pumps do I need? Where should the air separator be located? And I also have some basic system layouts. So these are the topics that we're going to be covering today. So I always like to start off with the phrases, I want to design a heating plant, but where do I start? Well, the simplest place is to start with a building. And in our case, we're going to use this picture on the right is the headquarters for the TripAdvisor headquarters building in Massachusetts. I don't know anything about this building. I love the picture. It's a great looking building. So I'm just going to make up stuff in the building. These things that I'm showing you about the size and the load is all made up for the presentation purpose. It doesn't actually, I don't even know what type of HVAC system is in this building. So we're going to start with a building, in this case, a simple office building. And our building is going to be, the picture is the TripAdvisor building in Massachusetts, and we're just using it because it's a nice looking building. We are going to pretend that this building is 480,000 square feet. And for the purposes of today's discussion, 480,000 square feet, we're going to have a heating load estimate of 30 BTUs per hour per square foot. So if I multiply 30 BTUs per hour per square foot times 480,000 square feet, I'm going to come up with approximately 14.4 million BTUs per hour. So that's the peak heating load that our heating plant has to satisfy. And if you notice, I put a little asterisk here because the actual heating load should be based on a detailed heating load calculation. You can use the TACO load tool. And the other thing is that for today's discussion, the load does not include any domestic hot water. So our hydronic heating plant is not going to be responsible for domestic hot water, just for the building itself. And here's the link to the software. I'm going to click on that right now. And hopefully with a little luck, it's going to go live to our website, TACO Comfort Solutions. And if you'll notice, if I scroll down just a little bit on the right-hand side here, you can see, I'm going to try my pen and see if that works. There it is. You can see on the right-hand side, there's the load tool. And if I scroll down a little bit farther here, you can see that you can download the TACO load tool. So if you want to do a detailed heating and or cooling load, you can use the TACO load tool. It's a free download and it's very easy to do. Okay. So that's where you can get the TACO load tool. But for today's purposes, again, we're just estimating the load to be 14.4 million BTUs per hour. And let me erase this little gizmo over here. There we go. Okay. Let's continue along. So when we talk about what type of fuel should I use, the first thing we want to think about is availability. And I'm going to cover each one of these in a little bit detail here. We're also interested in the cost, the heating value of the fuel, and whether or not the fuel requires any storage. So let's talk about availability. The fuels that we are interested in today are natural gas, propane, or fuel oil number 2. So keeping in mind that those are the 3 fuels that we're interested in, and we're interested in the availability. So as it turns out, we're going to be thinking about this building located in Massachusetts. And in Massachusetts, for the most part, at most sites, we have all 3 fuels available for our use or choice. We have natural gas, propane, and fuel oil. I have done other projects throughout my career where natural gas and or propane was not available. And the only source of fuel the only source of energy, rather, was fuel oil. And for today's discussion, I'm using fuel oil number 2. Okay, so that's the first thing that we have to think about. The second thing is cost. So we talked about availability. The second thing is cost. Let's talk a little bit about cost. Turns out that I did some checking this week, and natural gas in Massachusetts is about 95 cents per therm. And a therm is equal to 100,000 BTUs. And we'll see the heating values of these fuels in a moment. I have a little chart for you guys to look at. Propane is about $2.95 per gallon. And fuel oil number 2 is averaging about $2.10 per gallon. Now, these are average values that are available. When someone has a large building, they typically negotiate their fuel costs on either an annual or a multi-year basis. So, for example, I have the average cost for number 2 fuel oil is $2.10. If someone is negotiating with a fuel oil supplier, they may get their fuel oil for, I'm making up a number, it could be anywhere from $1.75 per gallon to perhaps something around $2.25 rather per gallon. But we're going to use these numbers just to kind of provide a point of reference for cost of fuel. And again, I got these numbers yesterday. I wanted to be up to date on the cost of the different fuel options. And here's a little chart that has the heating values for each of the 3 fuels that we are going to consider today. I grab my pen over here. And if you'll notice, for natural gas, the units are 100,000 BTUs per therm. That's how natural gas is sold by the therm. And as I said a moment ago, the natural gas, I believe, is about 95 cents per therm. Propane, right here, has a heating value of 92,500 BTUs per gallon. That's the heating value, the average heating value of propane. And for number 2 fuel oil, so I'll circle fuel oil up here, and then this little chart says for number 2 fuel oil, it's approximately 138,500 BTUs per gallon. Now, some people actually use 140,000 BTUs per gallon, but 138,500 BTUs per gallon is probably closer to the average. By the way, some facilities will burn number 4 fuel oil or number 6. And if you'll notice, the heating values for these fuels are even higher. So the heating value for number 6 fuel oil is about 153,000 gallons. So you'll find some large facilities will use either number 4 or number 6, but there is a trade-off, and that's why you have to check your local codes, because number 4 and number 6 have higher levels of sulfur in it. So number 2 is a more refined fuel. In terms of fuel oil, it's probably one of the cleaner fuels. Okay. I converted the cost for each of the three fuels that we're going to consider today into dollars per 100,000 BTUs. Well, like I said, the natural gas is 95 cents per 100,000 BTUs, which is a therm. And propane per 100,000 BTUs, based on the prices that I showed you a moment ago, is about $3.19 per 100,000 BTUs, and fuel oil number two is is $1.52 per 100,000 BTUs. So by making them all equal to 100,000 BTUs, you can see that in terms of in terms of cost of the fuel, natural gas is definitely the winner. And it's not just in New England we see this. We see this probably across the states. For those of you that are in the audience that are in different parts of the world, it'd be interesting to see in terms of US dollars what you are paying or what you think the average cost is for natural gas in your part of the world. So if you could type into the question area, and Brett will take a look at it. It'd be interesting to see what the range of costs for natural gas is all over the planet. I'm quite interested in that. So hopefully we get some feedback. Any feedback at all, Brett?
I will keep checking.
Okay.
Nothing yet.
Nothing yet. Okay, so now that we've established the cost of the fuel and the heating values of the fuel, let's talk a little bit about the next topic here, and that is fuel storage. So when it comes to natural gas, there is no fuel storage. You purchase natural gas typically from a utility, a pipeline. It's supplied to the building at a specific rate, rate meaning so many cubic feet per minute. And it's also delivered at a certain pressure. And I believe most natural gas for low pressure natural gas, I think it's around 14 inches of water column. And you can, in some cases, get high pressure natural gas, in which case you have to use a pressure regulator. So gas doesn't require any on-site storage. However, when it comes to propane, propane does require on-site storage, and in this case, I have put in 55,060 gallons worth of storage. In a moment, you're going to see where I came up with this number. And then fuel oil number two, I've put in 41,099 gallons. So under this first asterisk where I have propane, 55,060 gallons, that is not the tank size. The physical tank, when you're storing propane, has to be larger than the gallonage that you need. And the reason for that is that you have to have a certain amount of surface area and volume of gas above the liquid inside the tank to ensure that you have enough to evaporate, especially in cold weather. It has to be able to evaporate and feed the boilers at the proper flow. Okay, so how did I figure out the size of the tank? Well, I did this little calculation. I said the fuel oil storage, if our peak load is 14.4 million BTUs per hour, I divided that by 138,500 BTUs per gallon. That would tell me how many gallons I needed to burn per hour. And if the boiler had 85% efficiency, so let me just grab my pen over here. So this is the heating value of the fuel. You divide both by the heating value and by the boiler efficiency. And for the majority of fuel oil boilers out there today, they're probably in the range of 85%. Now you can get condensing fuel oil boilers and they would have higher efficiency. But for today's discussion, I'm just using 85%. So if you take that number, and that would be the number of gallons per hour that you would need for your peak load, and you multiply that by 24 hours per day, and then multiply that by 14 days, which is a 2-week supply. That's how you come up with the 41,000 99 gallons of storage. Now, the important thing to keep in mind is that I did not take into account, excuse me one second. I did not take into account any diversity that would take place. In other words, this is the peak heating load. And if the boilers were running at full capacity 24 hours a day, and I wanted to have enough fuel supply for 14 days, I would need roughly 41,000 gallons. But in the real world, to get a better estimate in terms of how much fuel you would consume, you'd want to look at charts that indicate the number of degree days or degree hours that are available for your coldest month. And typically that's either January or February if you're in the northeast of the United States. And then if you were in different parts of the world, you'd have to look at the degree days or degree hours. So in all likelihood, you probably wouldn't need 41,000 gallons because you're not going to run the boilers at peak load, especially during the daylight hours. So even in New England, during the design day, when the building is occupied and it has people, it has equipment like computers and the lighting, there's a certain amount of internal heat gain. And so the amount of heat loss that takes place, and also during the daylight, the temperatures are a little bit warmer, and also you get the sun effect. I don't know, Brett, is it sunny in New England today?
It is sunny, mostly
So you
sunny
get
today.
some solar heat gain. So you can see, at least in terms of the daylight hours, you're probably not going to need the peak capacity. And so that's the concept behind what you might do. So you probably don't need 41,000 gallons. You might actually need something, maybe even half that, in order to get a 14-day supply. Now, the other part about how much should I store for fuel oil storage is also how soon can I get a delivery. So most building owners will contract with a fuel oil supplier, and they'll have a guaranteed delivery within 2 days, 5 days, 1 week, that sort of thing. Now you'd say to yourself, wow, why would you have such a lengthy time, like a 1 week before you could get your delivery? Well, the concept there is that if you have a major winter storm, it takes a couple of days to recover from that storm and to get trucks back out on the road to make those deliveries. So that's why most facilities want at least a minimum of 14-day supply. Now, again, this is a simple office building. If you had a laboratory or you had a hospital, you'd probably have more stringent criteria that you would establish, and you might even want to have, instead of just a 14-day supply, you may want to have a month's worth of fuel oil supply. So it depends on the functionality of the building, what the actual load is, and the type of contract that you sign with your supplier. So any questions floating out there, Brett?
No, we did get some numbers. Alberta, variable rate of 0.2 cents per GJ applies through fiscal year 2021. Indiana, 1.54 propane, 35 cents USD per M3 natural gas. So we got some numbers, but anyways, continue.
Yeah, that's interesting. The numbers really fluctuate quite a bit depending on where you are. Okay, so one other thing I like to point out about other items for fuel oil storage. So if you opt for fuel oil for your building, you have to take into consideration that you need a fuel oil transfer pump system, because let's say you had fuel oil storage and it was underground. There are specific code requirements for fuel oil storage tanks underground. That's why I put the code issue up front. I won't review those, but ultimately you need to transfer that oil from the storage tanks to typically to a day tank. So a day tank is a relatively small tank that's inside the building. And usually the day tank is set up, and it could be as little as 200 or 300 gallons, that sort of thing. And the whole idea is to pump the fuel from the storage tanks to the day tank and then feed the boilers from the day tank. So you need to have fuel oil day tanks. You also have to have fuel oil piping, and you need a fuel oil capacity monitoring system. that tells you how much fuel oil is in your storage tanks. And the other thing is you need to have is a fuel oil leak detection system. So fuel oil has its complexities. So even though the fuel has a higher heating value than natural gas, it also has its storage and transfer complexities and monitoring complexities. And all of these systems have to be incorporated for a fuel oil storage system. Okay, so after all of those things, what's my fuel choice? It's natural gas. So I'm going to put a check mark next to that. And I went through that whole discussion to ultimately decide for this presentation, I've chosen natural gas. Okay. The next thing I like to put in is where should our boiler be located, our heating plant? Should it be at the top of the building, the middle of the building, or the bottom of the building? Okay, so let's have a very short discussion about what we mean by top, middle, and bottom. So when it comes to the top of the building, most people would put the heating plant, the hydronic heating plant, in some type of penthouse. So it sits up on the roof, and it's usually enclosed in a mechanical penthouse. Most jurisdictions, not all, but most jurisdictions will not count the height of the penthouse in the overall height of the building. So in most municipalities, the definition for high rise is somewhere between 70 to 75 feet. So if your building was 15-foot floor to floor height and you had 5 stories in it, it would be 75 feet. So it would not be over 75 feet. And so it would fall into the low rise category. So it would not be considered as a high rise building. And because the penthouse is not added to the height of the building for determining whether it's a high rise or low rise, then the penthouse perhaps could sit on top of the building, which is another structure, which would house all of your mechanical equipment in the top of the building. So that's one possibility. I've also designed buildings where the heating plant is in the middle of the building for a variety of reasons. It's not that unusual, especially in facilities that have relatively tall buildings, and sometimes they want to put their heating plant in the middle. And the other option is to put it at the bottom. So in this case, one of the advantages of putting it at the bottom of the building, since this is a heating plant, and you'll see in a moment I've chosen some temperatures, that there'll be a certain amount of hydronic static pressure that's available if your heating plant is at the bottom. So you'd have less concern about pumps cavitating, because you want the available net positive suction head to be greater than what the pump requires. And if the heating plant is at the bottom of the building, you wind up, whoops. Are we okay, Brett?
Yeah.
So if you have the heating plant at the bottom of the building, it simplifies the choice of pumps. It usually means that you have plenty of pressure, and you still have to do the net positive suction head available calculation and compare that against what's required by the pump. But most of the time, if it's a closed loop pressurized system that we're talking about here, generally speaking, you probably won't run into a problem if you put it at the bottom of the building. Okay. Erase that. So now, what is my choice? My choice is to put the heating plant at the bottom of the building. So I'm going to put a big check mark there. All right, so now we've made 2 decisions. We've said that we want the fuel to be natural gas, and we want the heating plant to be at the bottom of the building. So we've made 2 concept decisions. The other thing I like to put in there is that the boiler room ventilation and flue, that has to be determined by the code and type of boilers that you have. So what do I mean by ventilation? Well, specifically, there are codes that govern how to ventilate a mechanical room if you're using natural gas as a fuel, if you're using fuel oil as a fuel, or propane as a fuel. And again, you have to check with your national and local codes to see precisely what they need for ventilation. And then the flue itself generally is going to be dictated by the boiler manufacturer. And so whatever boiler you ultimately choose to put inside your building is to work very carefully with your boiler manufacturer's rep and find out precisely what type of flue system you need for that boiler. And they vary depending on whether they are condensing boilers versus non-condensing boilers and a whole range of options. So check out the code requirements for ventilation and flue, and also check with your manufacturer's rep for boilers to find out what they also recommend for the specific type of boiler that you're interested in. Okay. So what about the quantity of boilers? Well, one option is to use one boiler at 100% capacity, or load capacity. Now, one boiler has its pros and cons. One boiler is going to be less expensive than multiple boilers, but if the boiler should fail, you're going to be out of luck in terms of keeping your building heated for the winter. So that's one possibility. Another possibility is two boilers at 50% each. The concept here is that if one of the boilers should go down, you do have the second boiler, and for a significant portion of the time, one boiler at 50% will keep the building at least warm enough to accommodate on a mild winter day full occupancy and functionality of the building. And certainly at night, it'll keep the building warm enough so it doesn't freeze. So let's talk about another option for two boilers. Another option is two boilers at 67% or 2/3 capacity. One of the advantages of going from two boilers at 50% versus two boilers at 67% is that at 2/3 capacity, when you look at the load profile of a building, especially during occupied hours, 2/3 capacity for simple office building will probably handle more than 95% of the operating hours during the daylight hours. So for all practical purposes, if you should lose one of the boilers at 2/3 capacity, you probably have nearly 100% capacity for more than 95% of the daylight hours. Before I go any further in terms of other boiler combinations, any questions out there? I know it's a subtle difference between 50% and 67%.
We have a question about expansion tank and pumps, so I think I'll hold those off until you get a little further into your presentation.
Okay.
And there was a comment about the grade 6 oil, or whatever you wanted to call it. That potentially has to be preheated, right, to be used because it's so thick.
Yes, in most cases, depending on where you are, on the planet. Certainly, if you're in areas like Alaska, you have to heat that oil in order to pump it. Number 6 oil is very common for very, very large plants, like central heating plants, campuses, colleges, universities, especially in the colder parts of the country. And yes, you do have to heat number 6 in order to transport it. I used to work in shipbuilding design at one point in my career, and we used a fuel oil known as bunker C, which is very thick. It's like molasses, and when it cools to room temperature, it's like tar. And so, yeah, we had to have extensive fuel oil heating systems to transport the oil from one location to another.
And Bryce made a comment about another negative for one boiler is a potential for significant issues with cycling or inadequate water side flow to keep the boiler running. Good point.
Yes, that's an excellent point. I'm glad someone brought that up. So yes, if you have a single boiler, you could potentially have a short cycling issue. So that's an excellent point. Okay, let's look at the 3 boiler option. So one option is to have 3 boilers at 50%. That means if you lose one of the boilers, any 2 boilers would provide 100% of load capacity. And the other option for 3 boilers is 3 boilers at 33%. And the logic behind there is, yes, if you lose one of your boilers, then you only have 2/3 capacity, or 67%. But if you recall what I said a moment ago, especially in our discussion of a simple office building, probably 67% would handle the building heating needs for more than 95% of the hours. And the advantage of 3 boilers at 33% is now you can lose any one boiler and you probably have enough capacity to handle the overwhelming majority. The other advantage is you get nice turn down, because now that the boilers are 1/3 capacity, they're relatively small. Okay, so when it comes to my preference, I tend to like 3 boilers at 33% each. So I'm going to put a big check mark next to that guy. Okay.
I would think, Rich, that the size of the building would play into this thought process as well, you know?
Yeah, exactly. I mean, there are so many variations of boiler sizes and configurations. That's why I recommend you talk to your manufacturer's rep. That if you're in New England, for example, the folks at Emerson Swan provide expertise in several lines of boilers, and they can really help you figure out what the best combination of boilers and configurations would be. But for today's discussion, I like the 3 boilers at 33% each. All right, let's continue. Now we have a piping diagram. And in this first diagram, this is variable primary flow. So we have 3 boilers. We're using the concept of 3 boilers at 33% each. I get my pen over here. So I have 3 boilers at 33% each. So if I should lose any one of these boilers, if I just put a big X through there, again, I have 2/3 capacity. And in all likelihood, I'm going to be able to maintain my building, especially during the daylight hours, at 100% functionality. I might be running a little bit short on the coldest day of the year at night, but I would definitely, with 2/3 capacity, have enough to keep the building warm and to prevent anything from freezing. More than enough capacity in that case. And because it's a primary variable flow, you have to look very carefully at the requirements of the boiler manufacturer to look at the turn down ratio. So most boilers will probably easily have a turn down ratio of maybe around 20%, from 100% down to 20%. So if you take 20% of 33, you're down around 6%. And then if you look at that for the total load, that's a significant turn down that you can have. And other boilers have even better turn down ratios. So again, talk to the boiler experts and find out the best arrangement for your boiler and capacity. If you'll notice also, I'm using 150 degrees Fahrenheit for my supply water temperature and 120 degrees. And since my return water temperature is below 130, then I have the ability to use condensing boilers. And condensing boilers have much higher efficiencies. Their published values are anywhere between 95 and 99%. And so by having this temperature supplied to my building, I have probably the best energy arrangement, excuse me one second, the best energy arrangement I can have. Now, the implication here is that the terminal devices inside my building would have to be designed for an entering water temperature of 150 degrees. Most equipment has nominal capacity based on an entering water temperature of 180 degrees. So special attention must be given to all the terminal devices being used in the building to make sure that they have the capacity that you're looking for at an entering water temperature of 150 and a delta T of 30 degrees across that terminal unit. So if your building is going to be heated by fan coils, you have to have the proper fan coil selection, air handling units, the heating coils inside the air handling units, and perhaps either in-floor radiation or some type of wall radiation like baseboard or panel radiators. In Cranston, Rhode Island, we're using panel radiators on the external parts of the building, and we are supplying water temperature around 100 and I think it's around 160 degrees, and we have about a 30-degree differential. So our return water temperature typically comes back at around 130, which is within the range of our condensing boilers. Okay, so that's primary, variable primary flow. The next category, oh, this might be a good point to answer that question, Brett. What was the question on the pumps?
What are the advantages, if any, of placing the pumps in the middle of the building?
Well, there are advantages. There could potentially be advantages from a hydronic perspective, but if it's a low-rise building, which is the one we're talking about today, I like to consolidate all of the hydronic heating plant equipment in one location. I like to have everything in there, and the only thing leaving that central location would be the distribution piping to the terminal units, and we just outlined those terminal units. Perhaps they're fan coils, baseboard radiation, panel radiators, radiant floor, radiant ceiling, air handling units, that sort of thing. So I like to consolidate everything into one location. There could potentially be a benefit, but I think in general, it's nice to have everything in one location. Was there another question?
Yeah, I think this would be a good time to mention that maybe this drawing is for presentation purposes. People are commenting on some of the locations of stuff.
Yeah, so if you notice in the left-hand corner, it says not for construction. So I decided to add that disclaimer in there for that exact purpose that you're talking about, Brett. So
yeah, well,
yes.
I mean, you got the expansion tank and air separator located in one spot. Maybe you're pumping away from the boilers. Maybe you should pump to them. There's all different kinds of stuff there.
Yes, you're absolutely correct. And for today's presentation, I'm interested in sort of the general concept. If we were going to do an actual design, yes, we would refine the design and perhaps optimize the location for the expansion tank and the air separator. The way it's displayed right now, everything works. It just may not be the absolute optimization, but it's one way of looking at the hydronic heating plant.
So we have a couple of other questions that are probably pertinent right now. What is the acceptable range of temperature for condensing boilers?
Well, in general, you want the return water temperature to be below 130 degrees Fahrenheit. And in order to take advantage of the lowest pumping capacity in terms of GPM, it's nice to design a system with a delta T of 30 degrees Fahrenheit, which is why the criteria that I use, I wanted a return water temperature below 130, so I picked 120. I added 30 to that to 150. So I'm taking advantage of a relatively high delta T to reduce the amount of pumping horsepower, and also to make sure that I was well below the condensing range. And generally speaking, the condensing range temperature, return water temperature, is less than 130. So I've accomplished both tasks by having 120 to make sure that I could take advantage of condensing boilers, and that I had a supply water temperature just 30 degrees above that. Hopefully that answers that question.
Yeah. And then this is a good question too, or clarification. Are you referring, you show your boilers at 33%. Are you referring to the boilers running at 33% of their own capacity, or 3 boilers running at 100%, each carrying 33% of the building load?
It's 33% of the building load.
Yep.
So in our case, I believe it came out to the building load. Let's do the quick math here. The building load is 14.4. If I divide that by 3, that's about 4,800,000. Yes, so each boiler is 4 million just under 4,800,000 BTUs per hour.
Yeah, you would want to run the boilers almost at 100% of their capacity, not 33% for sure.
That's correct. So in other words, this boiler right here, let's say I'll just circle it. This little guy right here, if your load had dropped off in the building, so as each one of these other boilers would shut off, you're running this boiler at 100% of its own capacity, which is 33% of the building demand. And now if you had a turn down ratio of 20%, 20% of 33% is around 6%. Does that make sense? Any sense?
Yep.
Any other questions?
No, proceed.
Okay, and so now we'll look at another option here. Let's erase this.
We have about 15 minutes left.
And okay, so the last option here is for primary secondary piping. In this arrangement, the boilers are fed by their dedicated pumps. Let me just get a pen again. So here's each boiler pumping arrangement right here. And again, that becomes the primary loop. Generally speaking, when we refer to the primary loop, we're talking about the loop that is served by the heating or cooling equipment. So let me go back here and circle the whole system here. So we're using a hydraulic separator right here. And so all of this piping, pumps, boilers are part of the primary pumping system right here. And then everything on the other side, this is going to be a bizarre little bubble here, but everything over here, everything out here, this is going to be the weirdest bubble you ever saw, Brett.
It's quite a bubble.
Yeah.
I like the
Everything
bubble.
out here. Everything out here is part of the secondary side of the system. So I'm going to erase that because it gets a little confusing. So we have the primary and the secondary part of the system.
It looks like the bubble I blow when I'm drooling at night, for God's sake. It's tough to get old, Rich. It's tough to get old.
Well, you know, I wasn't going to say anything, Brett.
I know. Thank you. I appreciate that.
Okay, so here are the pumps for the secondary side of the system. So this is probably more common in terms of what you see for existing boiler plants. They tend to be primary, secondary, and the reasoning behind that is because older boilers wanted to have relatively constant flow. Modern boilers have the ability to have variable flow. So in a primary, secondary loop, typically the primary loop, which is again this whole section over here, I'll put the letter P in the primary loop, and then in the secondary loop, I wonder if I can use my pen over here. Can I make an S over here? Look at that. In the secondary loop, it's variable flow. So one of the advantages of the primary secondary loop is that if the boilers are looking for primary, a constant flow on the primary side, this accomplishes that quite easily. And so now the only reason that you would have minimum flow on the secondary side is typically to protect the pump. If you had minimum flow requirements on the primary side, that's typically to protect the boiler. Generally, in the primary side of the system, the boiler determines what the minimum flow would be and not the pump. In the secondary, generally the terminal devices don't really care about minimum flow. They certainly would care in terms of capacity, but not in terms of operational characteristics. And so the limiter on the primary, secondary side would be the pumps themselves. And again, this is a simple office building. So our concept heating plant, again, is using pumps with 33%. If you should lose one of these pumps, you're going to have 67% capacity, like we talked about earlier, which would handle the building from during the daylight hours, probably more than 95% of the time. Okay, so let's erase all these wonderful bubbles and letters. And then we get to my decision. For today's discussion, I have selected the primary secondary flow. That's what I want for my hydronic heating plant. So let's summarize all the stuff that we've made concept decisions on. We've decided that the load is approximately 14.4 million BTUs per hour. We've made the decision that it should be natural gas. The boiler plant location is in the bottom of the building. We're going to have 3 hydronic boilers at roughly 4.8 million BTUs per hour each. That's 33% each. We have a hot water supply temperature of 150 degrees, and a return water temperature of 120 degrees Fahrenheit. We've decided on a primary secondary flow, and we're going to have 3 primary hot water pumps at 33% each, and 3 secondary hot water pumps at 33% each. So we've gone through the thinking process and talked about the different options for each step of the way, and we've come up with a heating plant concept design, and these are the decisions that we have made. Okay, now for my favorite slide. Any final questions out there?
Yes, so let's work some in here. So when you were choosing the location of the boiler plant, does the expansion tank get much larger if heating plant is in the bottom of the high rise?
Yeah, so when it comes to the location of the expansion tank, in our presentation today, it's a low-rise building, roughly 5 stories tall. So the expansion tank would have a slightly smaller expansion tank if I put it at the top of the building. If it was a high-rise building, say it was 30 floors or 40 floors, then if my heating plant was at the bottom and I moved the expansion tank to the top, it would have a substantial difference in the size of the expansion tank. However, with every decision like that, there are pros and cons. If I put the expansion tank at the top of the building and there's no other major pieces of mechanical equipment, I'd have to have enough structure in the building to accommodate the weight of the expansion tank if it became waterlogged with water. So, and I don't know the exact size, but let's say you had somewhere around a 500-gallon expansion tank. You have to assume that in terms of weight, that if it's a bladder style tank and if it was, say, a full acceptance tank, it could become waterlogged and the 500 gallons would fill up 100%. And we know that water weighs about 8.33 pounds per gallon. And if it was 500 gallons, that'd be about 4,000 pounds. So you'd have to carry that weight of 4,000 pounds to the structure of the building. So the tank gets smaller, but you may have a penalty of structural components to accommodate the tank at the top of the building. Next question.
Yes, we have a great question from Marissa. Question/comment. Are you supplying the 150-degree water temperature because of Legionella? Did that come into your thought process at all?
Well, in general, the temperature for Legionella is around 140 degrees. So I wanted to make sure that my hot water distribution system was at least was greater than 140, which is why I picked 150. And as I said before, with a 30-degree delta T, I knew that I was well within my condensing water range. So yeah, that's one of the reasons that I picked that temperature.
Excellent, excellent. All right. Does the hydraulic separator, which is used, have to have different supply water temperatures? Did you put one on your drawing?
I did. Let's go back. Let's see if I can find that here. Let's see. There is the hydraulic separator. Yes. So in this case, if the primary flow and the secondary flow are equal to each other, then the temperatures would be the same. Essentially, in a primary secondary loop, when the flows are equal on the primary side and equal on the secondary side, there's no flow that goes through the bypass. It's as if the hydraulic separator wasn't even there.
Excellent. I think we're winding down with questions. A lot of people are questioning, or asking, do you know the cutoff of when to go with 3 boilers or 2 boilers at 33% or 67% instead of 50%? Is there a cost savings, or how does it affect the terminals if you go condensing? I guess that's some more questions that are kind of more involved to answer.
Well, actually, that's why I specifically did not include that kind of information in this presentation. And the reason for that is because the boiler manufacturers reps have that expertise. They know their boilers inside and out, and they know what the benefits would be for a boiler that was sized, for example, for 33% versus 50%. They know what the control strategies are, and they have a wealth of knowledge. And that's why I strongly recommend that when in terms of concept, you could arrive at the same concepts that I have today, and then talk to the boiler manufacturers reps. And once you get some more detailed information from the boiler manufacturers, you may decide that, hey, you know what? I don't need 3 boilers at 33%. I'll have some other combination that will give me the best return on my investment.
There's a couple of statements about maybe not being as concerned about Legionella because it's a closed loop space heating design. So that's maybe a point we may want to at least mention. I don't know if that's true or not, but this is a great question. I have 2 more questions, Rich. The Delta T, what would your general recommendation? I see 20, I see 30, I see 40 for a heating system. Do you have a run of the number that you're used to?
Well, again, Delta T becomes a function of both the terminal units in the building. The higher the Delta T, typically the more surface area that you need in order to accomplish that Delta T. And so the more expensive the terminal device. So now it becomes engineering economics. So, if you have, let's say you had a fan coil system, and each fan coil had an entering water temperature of 150 and a return water of 120 at its design capacity. Well, if I supplied that terminal unit with a higher supply water temperature with a lower delta T, then I would not need as much surface area, and so the terminal units would be less expensive. So it's always a trade-off. So one of the issues has always been in our industry is that the more energy efficient the system, ultimately that translates into more surface area, more material, and more first cost. And so that's where the whole economic analysis comes in terms of trading off the temperature differentials against the additional cost for terminal devices and perhaps additional cost with boilers in order to accommodate those high delta Ts. The trend today is to go in the range of between around 25 to 30 degrees. Although, I think I've seen designs where people are using 40 degrees, but you have to pay attention to the details and not box yourself in.
One other question or comment, and shame on us, Rich, for every presentation not bringing this up. Which systems or which components on this drawing right in front of us does TACO sell? Why don't we put a check mark next to those?
Well, the good news is color coded, and everything that's green on here is equipment that we manufacture and provide. So we provide the multi-purpose valves, the pumps, the hydraulic separators, the air and dirt separators, the expansion tanks. Although not shown on this drawing, we also provide end suction diffusers. And if necessary, if somebody wanted to do storage, we could do buffer storage tanks. So what we tell people—
controls. We even have some controls, although
we even have
boiler controls.
When it comes to a heating plant, we provide everything in the heating plant except for the boiler and the pipes.
Yep, pretty much. Much
everything.
So feel free to specify us or make us basis of design. Anyways.
Well, hopefully, before I turn it over to you, Brad, I think we're just about out of time.
Yeah.
I just want to say thank you, everyone, for participating in today's discussion. We had a great great turnout. I think we had almost 500 people.
Yep.
And thank you so much for participating and listening to our presentation. Whoops, I have to shut the phone off.
Oh, you know what that means? You got to pick up milk and bread on your way home. Oh, you are home.
That silly phone always goes off when you least expect it. So at this point, I'm going to say thank you and turn it over to Brett. Take it away.
Thanks, Brett. Thanks, Brett. Thanks, Rich. Appreciate it. Everybody on the call or on the webinar, thank you so much. A lot of great questions. If we didn't get to them, we'll answer them offline directly to you. And just remember a couple of things. Most important is the recording or of the session, as well as your PDH will be sent out in an email tomorrow. If you have any issues, just send an email back and we'll make sure we'll clarify those on them. And then our next commercial one in February, oh my God, I can't wait till winter's over up here in the Northeast anyways, is going to be on doing some type of layout, piping design for chilled beam system. Maybe a little different than what you're used to. We're going to use that software that many, if not some of you, most of you have seen before. And we're going to have some assumptions and we're going to design a system. Let's learn together on this one. But it's a little different type of piping layout. We're going to think outside the box. We like thinking outside the box this year. 2021 is a thinking outside the box year for all of us. So again, thank you for your time. Stay safe out there, and we will see you hopefully next month. Take care, everybody. Thank you.